In this video, we are going to talk about physical modeling, what it means, and how to use it to develop a mathematical equation to eventually solve a problem. At the beginning of the year, a virus changed all of our lives. The disease caused by the virus spread from China to different parts of the world. It reached our country in February, and the number of cases slowly increased. This is a new virus, and our bodies do not know how to react to this. We have no idea how to stop it from spreading. One of our best approaches in order to examine the long-term effect of the virus is to model its behavior over time. By taking a look at the number of cases per day, we can develop a mathematical model to study its current behavior. From the model, we can then determine a mathematical equation that will help us predict what will happen in the future. This is how modeling works. A mathematical model can then be broadly defined as a formulation or equation that expresses the essential features of a physical system or process in mathematical terms. It can be represented as a functional relationship of the form as shown. Dependent variable is equal to a function of the independent variable, parameters, and forcing functions. In the case of the coronavirus, the mathematical model is simply an exponential function that is a function of time t. The constants a and b are computed based on the given data. It is from the constant b where we can get the doubling time. The doubling time is the number of days it takes for the number of cases to double. This is the basis of our scientists in determining how many new cases will arise in the next day or in the next month. Ideally, we want a high value for the doubling time. We'll learn more about this specific mathematical model in our lessons as we progress. Let's take a look at our modeling function and define a few things. In the coronavirus model, the dependent variable is y, which is the number of cases per day. The independent variable is the time, or specifically, the day. The parameters are not defined in that model as it is, but we can name a few parameters that could affect the mathematical equation. These are social distancing, wearing of face masks, lockdowns, and contact tracing, just to name a few. It is extremely difficult to assign these parameters into the coronavirus model, since these describe human behavior, and human behavior is very unpredictable. There is no forcing function in the coronavirus model that has an effect on the system. Let's take a look at a much simpler model, that is, the falling parachutist. How do we model a person falling down with his parachute open? First of all, what information do we want to know about the falling parachutist? We definitely would like to know where he is at any time and what time he'll be reaching the ground. What information do we know? We know that the reason that person is falling is because of gravity. So we know that the acceleration due to gravity g has to come in somewhere in our model. We also know that there is a drag force by the parachute that lessens the velocity of the parachutist's fall. How do we know that it lessens the velocity? From experience. That's why parachutists don't break their bones as they touch the ground, because the velocity is much lower with the parachute open. But how do we model the drag force? Since we know that the velocity decreases with an open chute, then the drag force has to be related to the velocity. The simplest mathematical relation that we can do is to make the drag force proportional to the velocity. At this point, you may ask me if it's a correct model. I can tell you that at this point, I really don't know. I am simply guessing. But our current theory is that the drag force is proportional to the velocity. By doing numerical calculations and comparing to what is happening in real life, do we know if our model or our theory is correct or not? Well, it turns out from numerous experiments that this model is correct for low speeds. For higher speeds, the drag force is proportional to the square of the velocity. Is the speed of a parachutist falling down considered low speed? It actually is. The problem of determining his velocity and position with time begins with the use of Newton's laws. We have two forces, the drag force on the person by the parachute and his own weight. Using Newton's second law of motion, we can then relate these two forces as shown. We have earlier modeled the drag force to be proportional to the velocity. Mathematically, we can write F is equal to CV, where C we call the drag coefficient. Since we know that the acceleration is just the derivative of the velocity with respect to time, we end up with this differential equation. This is easily solvable, and we derive the equation for the velocity. We can derive the equation for his position in the same way. Let's take a deeper look at the equations. Beginning with Newton's second law, we see that if we set the acceleration to 0, we can equate the weight with the drag force, giving us V is equal to mg over c. What is this velocity? It is the velocity when the net acceleration is 0. If there's 0 acceleration, then this velocity will no longer change because there is no net force. Thus, this is the maximum velocity that the parachutist achieves. It is also called the terminal velocity. We can then replace our final equation for the velocity with the terminal velocity as shown. So what then is happening to the parachutist? As he jumps off the plane, if he opens his chute at the same instant, his net acceleration decreases as his velocity increases. This is because the drag force increases as the speed increases. Then when he reaches terminal velocity, the drag force is just equal to the weight, and his acceleration becomes 0. In reality, parachutists don't open their chutes until before a certain altitude. They open them after a certain time. So there's a time t equals 0 from the moment he jumps off the plane until he opens his chute. During that time, his body also has a drag force. That drag force forces him to reach a terminal velocity. That velocity is extremely high and fatal. That's why he would still need a chute. And that's what I am going to show you next. For this demonstration, I am using MATLAB. So what I've done here is that I programmed the parachutist to open his chute at a specific time. I set the time to 15 seconds. Before that time, while he is in free fall, his speed increases, almost up to the terminal velocity. You'll also notice that his acceleration decreases, that is, the absolute value of the acceleration. And that's because his body also causes a drag force due to air resistance. At 15 seconds, his chute opens, and then his speed immediately decreases. His acceleration becomes positive and increases by as much as 3 times, and then starts to decrease. The positive acceleration is good and what is causing his speed to decrease. Watch the video carefully and pay close attention to what I just said about his behavior. You can replay this video as many times as you wish during your free time. Another type of physical concept that I would like to show you is the double pendulum. The double pendulum can be used to model numerous applications. One example is the movement of your arms. If you notice, your forearm and your upper arm are quite similar to the double stick that you see in the double pendulum. You can also model how you walk with your legs using the double pendulum. All you will need to do is to add a few restrictions, or what we call in physics as boundary and initial conditions, to mimic the movement of the arms and legs. This is actually a very simple system mathematically described by two ordinary differential equations, and is only complicated by the fact that you are using four sets of variables. I won't go into the mathematical details, and I'll just leave these out to show you. Instead, I'll show you how a double pendulum behaves given an initial condition. You can see how its movement closely resembles how you would move your whole arm. It would even seem like the double pendulum is dancing. You'll be seeing the double pendulum problem again when we discuss ordinary differential equation. In fact, this model will be included in one of your machine problems. I hope you've caught up with our video lesson for today. We set out to define what a physical model is, and I believe we've done that. We've also learned how to develop a physical model. We've used the coronavirus spread as an example, as well as the falling parachutist. You've also been introduced to the double pendulum, and I hope that you are looking forward to numerically solving the problem yourself. You've also been given a preview to what MATLAB can do. In this presentation, MATLAB was used to solve ordinary differential equations, describing the falling parachutist and the double pendulum. The solutions were shown in a graph and in a movie, both of which can be done in MATLAB. In the next video, we'll begin our tutorials in MATLAB and Python. We will be focusing on the material we most need in this course. These are mostly mathematical tools. I hope today's lessons have inspired you to learn more about computational physics. See you in the next video!